Welcome back to nonlinear structural dynamics. Somebody actually convinced me that psychologically it is more reasonable to see somebody, so that is why I have my video on from now on, and you see me even if it is just a small box within the main window. And our topic today is single degree of freedom systems, self-excited oscillations. And you know already this quite famous example of flutter vibrations of airfoils, and I think you've even seen this video several times already. So you see that there are some substantial vibrations that actually occur for this airfoil, and luckily this does not lead to any structural failure. So you know already it's a self-excited vibration, but for now pretend that you haven't, so that we systematically deduce this, and so pretend you don't know anything about this system so far, just have seen this video. And we're not so surprised about the form of the vibrations. It's just a harmonic oscillation, which we've seen, for instance, for conservative oscillations. We've seen that also for forced vibrations under harmonic forcing. So this is not really surprising. But we can rule out both, because free oscillations would need some initial energy. And where would that come from? It could come from an initial impulse, so a mechanical impact, but this isn't happening here. Also, it could come from some form of aerodynamic forcing that is like an impulse. So for instance, if there's a strong gust at some point that's just experienced once, this would have a similar effect as an impulse. Or if the aircraft lands, we would see something like that, but apparently this isn't happening. And also we can rule out conservative oscillations for another reason, because the free oscillations would not be conservative. We've discussed last time about sources of damping, and there is some damping always present. It can be in the material itself, it can be in mechanical interconnections, especially dry frictional dissipation in joints, for instance. So this will always be present and would lead to a decay of the oscillations, but apparently this isn't happening here. So these cannot be free oscillations. Forced oscillations could be, but we would have to have an external forcing that has a certain explicit imposed time dependence. This could come, for instance, if from a turbulence. So if the aircraft flies through a pressure field that is inhomogeneous in space and it flies through that, then it would see a dynamic force due to this. But let me assure you, this is not the case here. The flow velocities the pressures are quite that we see in front of the aircraft are quite constant. So this does not explain it. We don't have any forced vibrations. So what we can say is that in the absence of this, what we would expect is that we see this static equilibrium, right? There are some static forces, gravity, some aerodynamic lift force. This should lead to a certain static deflection, and this should be constant, but it isn't. So we have an unstable static equilibrium. And in linear structural dynamics, we saw that there are two types, or two ways in which we can lose stability: a monotonic divergence or an oscillatory one. And quite apparently this is of oscillatory nature, so it is linked to a dynamic instability. So effectively some negative damping ratio associated with this mode in the neighborhood of the equilibrium at least. And finally, about the energies, we can say that there must be some form of energy source that leads to these sustained vibrations, because quite apparently the amplitudes do not decay, although we know that we have some inevitable dissipation. We just discussed this about mechanical connections material. So there needs to be some energy source that supplies the system with energy. Quite apparently this is the flow, right? This is the source of the energy. And the way the system gets energy from this is not imposed by oscillatory external forces, so no imposed forces, but actually the system supplies itself with these energy source by itself. So because it vibrates, it draws energy from this source. So these excitation forces are due to the vibrations themselves, quite in contrast to external forces in the case of forced vibrations. So this is the well-known bending torsion flutter, actually, that you see here in the airfoil. We will in the following discuss a very simple prototype that is not really linked to this bending torsion flutter, but to other types of dynamic instability that can occur also for aerodynamic or aeroelastic systems. So actually we are considering this setup here of an airfoil that is exposed to a constant velocity here of the flow. Think of a wind channel or wind tunnel, and this airfoil can move only vertically. It has a certain mass. It also has a linear spring here. And very special about this system is the viscous damper here, which is attached not in the direction of motion, but actually transversally to that. And if we do the force balance here, we see here that we need a balance between the inertia forces, the forces due to this damper here, the linear elastic forces, and the aerodynamic forces. Let's discuss about the aerodynamic forces first. So here we just have the dynamic pressure. We have here some effective area and essentially the lift coefficient, which depends on the angle of attack. Let's assume that the angle of attack, in the absence of any velocity here, so that in the stationary case, is 0. Then this can only change because of quasi-static aerodynamic effects. So if if we have certain velocity here in the vertical direction, we can draw this triangle here. So we have a vertical velocity q dot, we have a horizontal velocity of the inflow of this v here, and then we see that this is the relative velocity that the airfoil actually sees. So this will be here, this alpha here will be the effective angle of attack, and if q dot is small, we can approximate it by this this ratio, q dot over v. So then we need the lift coefficient as function of the angle of attack, and this generally can be expressed as a polynomial or a Taylor series expansion, and we here assume that we can neglect higher order terms, and also this constant component here would lead to a static force, and we will for simplicity just assume that this is compensated by this spring. So this q, we could determine the equilibrium position first and then do a replacement of variable or variable transform to measure the dynamic displacement from this equilibrium point on. Then we would get the same result as taking the shortcut and simply ignoring this static component. One thing is that still we need to assume that in this static equilibrium position, this damper here is horizontal. Now let's discuss about this force. So we measure here by this FD the vertical component, so in the direction of motion. This the force stemming from this element here, and this is apparently here damping times the length change of this element. This is the velocity, basically the relative velocity between the 2 points, the endpoints of this damping element. And this is the whole force acting in the direction of this element, but we are only interested in the vertical component, which is apparently this times sine of this angle here. So we need to further develop these two terms. First, this angle here is in accordance with this rectangular triangle just Q over L, and L is the sum here, the geometric sum L0 squared Q squared square root of that. And L dot is then the time derivative of exactly this expression, which leads us to this here. Now if we put both together, we basically have d times q squared, q dot, and then in the denominator we have this square root times this, the same square root. So in the denominator we have L0 squared q squared plus q squared. Now we can simply assume that if, as assumed here already, that, no, actually this is q dot, this is q. Let's assume q is smaller, much smaller than L0, then we can simplify this and this denominator to L0 squared. Ignore the plus q squared. Then we get this term. We could also take the formal way over a Taylor series expansion of appropriate order, which would also give us this. Now we put everything together, then we get this. So both terms here, this delta zero leads to this aerodynamic damping, which is linear, but it's interestingly negative. And then we get some, well, it's not really easy to say, it's because it's an essential nonlinear term, so it's not easy to say if it's positive or negative, but it is essentially nonlinear. There's no linear counterpart to that, or linear component to that. And this comes from this mechanical viscous damper here. So with the force balance between elastic forces, aerodynamic forces, viscous damping forces, elastic forces, and the coefficients are like this. This form of equation is called a van der Pol equation. And if Duffing is really one prototype for all sorts of nonlinear, all sorts of nonlinear systems, and nonlinear stiffness, with a nonlinear stiffness term, then another prototype in nonlinear dynamics and nonlinear vibrations is the van der Pol oscillator. It actually was initially derived for electrical circuits, but it describes actually many phenomena in natural science and engineering, including this particular system here. Now, one caveat about this mechanical oscillator is that we have 4 distinct parameters, and what's normally done is then a dimensional analysis in order to get rid of the parameters, to get some dimensionless parameters that are that are somewhat meaningful, and this also simplifies the transferability of the results. You really see what the response depends on, and this can first of all be achieved by dividing by one of the coefficients, and secondly by time normalization. Time normalization can here simply be done by using the natural frequency of this underlying conservative spring mass oscillator, linear spring mass oscillator, I should say. And this leads us to this. So this is actually the standard form of the van der Pol equation, and we will also use this later when we do some parameter study on this. But for the following derivation, we will also use this form of the mechanical oscillator equation, because it is somewhat more intuitive. This is really the drawbacks and advantages of normalization. So we arrive at a minimal set of parameters. That's definitely a bonus. So easily we can transfer the results, but here every parameter is very clear. Mass, stiffness, this delta zero is defined as shown here. All very intuitive and clear parameters. Alpha and beta are much more difficult to physically grasp. Of course, with some creativity you can think of something here. but that's why we will actually use these two. So let me write down the van der Pol oscillator equation once again. So that will be our motivating example. So the equation reads like this. So we have some inertia terms. We have a negative linear viscous damping term and some nonlinear term here going with the square of Q. And then we have the linear elastic forces, and then everything is zero, so that we have still an autonomous system. And we will assume that the coefficients here are all positive. So mk obviously are positive, delta 0, delta 2, all are positive. And what we see here is a damping-like term. So usually we would expect here in a linear sense, we would just expect here a positive constant, which explains the positive viscous damping, but here it's more complicated than that. So first of all, if Q is very small, then this delta 0 here will dominate, so we just have a negative damping. However, for very large Q, so obviously Q will oscillate, but its square will have a non-zero average, right? If this can only be positive, and even if it oscillates, it has a zero mean, and it has not zero mean. So at some point, at very large oscillations, we would expect that most of the time in a vibration period, this term here dominates. So if we neglect this, then this leads to an effectively positive damping. And somewhere in between, maybe there's a balance between the two. So we have effectively damping 0. And that's basically the limit case that we already, by just looking at the equation and knowing that the solution will be a harmonic oscillation, can already suspect here. Of course, we will analyze this mathematically, quantitatively as well. So for small q, let's just write this down. So where delta 0 is much larger than delta 2q squared, so effectively we have a negative damping. On the other hand, for large vibrations, large oscillations, delta 0, this sign here just switches, and we have positive damping in average. So there's an intermediate case conceivable. Where positive and negative damping cancel an average. But how exactly is, of course, the question. We need to determine the actual amplitude and the precise behavior at of this intermediate case. Essentially, we know that, at least in the video, we saw some harmonic oscillations of constant amplitude. So we suspect to get a harmonic response, and we suspect that we have a finite amplitude. But of course, in order to say whether this is critical or not, we need the amplitude. So it's just a motivating example. So from now on, we treat a more general situation. So we consider the general autonomous single degree of freedom oscillator. So again, we have inertia forces. And now we extend, compared to the conservative case, we extend this term. So this is not only a function of q, but now we have also the dependence on the velocity. This is now a difference to the conservative case. And we will see how this changes the picture, in particular how this changes the energy balance and power balance. And in order to analyze this, we again multiply by the velocity. So forces, generalized forces times generalized velocity lead to powers. And the powers are, of course, the time derivative of an energy quantity. So what does this lead to? So 0 times q dot is still 0. Here we know this term already. That's just the time derivative of the kinetic energy. Ek, kinetic energy. Now this term here is a little bit more complicated. We know what happens in the conservative case. This is then a term that we can consider as the time derivative of a potential energy. But that was the case where these forces here, these, let's call it general nonlinear restoring forces, these we could derive from the potential. So this f was just an f of q and could be expressed as the derivative of a potential with respect to the generalized coordinate. Now, this is not possible anymore, but the idea can be to split this into a conservative and a non-conservative part. And the idea will be that we don't go into the system and look for sources of conservative, non-conservative forces. That's a little bit cumbersome, and we want to we seek a formal way to introduce conservative and non-conservative terms precisely by looking at this expression here. So we will split f of q and q dot. We split this into a term f of q and 0, so where we substitute 0 for the velocity, then we have f of q dot minus f of q and 0. So this is just the addition of a smart 0, as I like to say. So this first term here now just depends on q. So this is exactly what we had in the conservative case. So we can just say this is g of q, so it's just a pure function of q, and we can take the same idea as in the conservative oscillation case and define this as the gradient of a potential energy. So this is dEp dq. So we can integrate this to a potential energy and consider this as the gradient of a potential energy. No problem there. So if this is the conservative case, so by definition conservative forces can be derived from a potential, and this makes this the non-conservative forces F and C, which now do depend on q dot. If they don't, if there's no dependence on q dot, we directly see that this is zero, right? If it doesn't matter that which value for q dot we put here into the bracket, then this will give us zero. So yeah, this is a nice thing. Also, this for q dot equal to zero, this also gives zero, right? This is also an interesting finding. So if the velocity is zero, this expression gives us zero. And this NC here stands for non-conservative. So as opposed to these, which are conservative, they are derived from a potential. And this splitting here is without loss of generality. One idea or one statement one can make here: why do I put q dot or the argument q dot to zero here? There's some ambiguity. I mean, the splitting works also for a non-zero value, but I want basically I want this to be zero, this non-conservative force to be zero if the velocity is zero. So at the equilibrium point, I want this term to be zero. Makes sense, right? So yeah, that's really the idea. So, actually, I want this statement here. And this is just how we usually defined equilibria, by setting the conservative forces of the underlying conservative system, by setting this restoring force to zero. Now we can indeed reply to this question mark and say that this is partly this here, the gradient of the potential energy times q dot. So dEp dq is simply this g here times q dot plus F and C q dot times q dot. So we can interpret this now, this term here, as the time derivative of the potential energy, which of course only depends on the coordinates, not on the velocities. And this here is simply the power supplied or dissipated by non-conservative forces. So this is nice. So we can more explicitly write down the energy balance. We can summarize mechanical and kinetic and potential energy to the mechanical energy. So the time change of the mechanical energy, that's what this equation says, is balanced by the power supplied or dissipated by the non-conservative forces. And we can of course write this also in integral form and say that the sum here, actually let's write it like this, at a certain point in time, at time t, minus the value of this at time t0, so the initial energy, that's the integral of P and C. Okay. Now this would be the initial energy here. That's the initial energy. So the energy at a certain time is then, or the difference in mechanical energy from a certain time on is then the integral of this power. And when we think a bit about the oscillation that we saw in the video, we saw it was, to a good approximation, periodic. So we can think of what happens in that case. So if we have a periodic behavior, then and we do this energy balance over one period, then this small t here is the capital T, the period length. Then obviously, because of periodicity, the mechanical energy needs to be the same after one period. So this means this integral has to vanish. So for a periodic oscillation, we know if we integrate here the non-conservative power, let's write here T also in the argument, it must vanish. So period T, of course. So we can say that supplied and dissipated power cancel in average. In average, because this integral here just determines the average value of this power, actually multiplied by the period length. If we were to determine the actual average value, we would divide also by t, but if it's 0, it doesn't matter. So supplied, this requirement says that supplied and dissipated power cancel in average. Good. So this is basically a method to determine the amplitude, if we want, of a periodic oscillation under these actions of non-conservative forces. So if we assume a certain periodic oscillation of a certain frequency, of a certain form, we can then substitute this into this integral and determine or evaluate this value here as function of the amplitude in order to determine the amplitude essentially of this oscillation. So one finding we need to make here is that as opposed to the conservative case, we cannot eliminate time from this condition here. We were able to do so in the conservative case because essentially we said that the kinetic and potential energy, they don't contain time explicitly, and actually this is a conserved term, but this does not hold in the non-conservative case. So that's the difference. And let's just put here the idea that I outlined to find a solution. The form of time dependence must be known or assumed. So if we want to use this particular expression to determine the solution, or an approximation at least. And the point is, of course, if we don't know the exact form, we can take a lucky guess, but in general this will not be the exact solution. So we need to approximate, or we need to live with an approximation. So what do? Quite generally, if exact solution not available to us, we need to approximate. And the simplest approximation, then that's what we did throughout linear structural dynamics, was to linearize. So we know already what will be the outcome, but because it's so important, let's still formally do this here. Linearization of f q dot around the equilibrium position, and the equilibrium is still q equal to 0 and q dot. And actually this was the case for our example, but let's actually formally require this, that if we substitute q equal to 0, we q and q dot equal to 0, we require that this is in fact an equilibrium position. We can always redefine q so that it counts from an equilibrium position. So that's actually require this without loss of generality, so that we can formally do a Taylor series expansion. So f of q dot is now f evaluated at the expansion point, so f0, 0, df dq q plus df dq dot 0, 0 times q dot plus some higher order terms. And we do a linearization, so this here is approximated as 0 by definition. We know that, or we require that this is an equilibrium point, so the restoring force needs to vanish. So we have these two terms here, the gradients of q. And just for the van der Pol oscillator, actually, we can do this. So this two Fourier expansion, so f of q dot is, if we go back here, is everything except for the inertia terms here. So we go back up here. So everything from here. So let's just copy it here. So we have minus delta 0 delta 2 q squared, q squared q dot kq. So the linearization of the whole equation actually will be mq dot dot plus. Now we basically have this this term here, which is 0, and we have then the gradient with respect to q. So the gradient with respect to q is here this plus delta 2, actually 2 delta 2 q dot plus k 0 0 q, and then everything derived with respect to q dot gives us minus delta 0 plus delta 2 q squared 0 0 times q dot equal to, this still needs to be equal to 0 in the linear case. So what does it give us? So if we substitute 0 0, and this term here vanishes, and here we get just the minus delta 0. So we can write down this, and we know exactly what is the outcome of this equation. This is a single degree of freedom spring mass damper oscillator with a negative damping, as we assumed delta 0 is 0. So we know what the solution is. Either we have subcritical or supercritical damping. Let's say we have subcritical damping, so the damping ratio we get out of this is smaller in magnitude than 1. Then we have an oscillating divergence. In any case, we have an exponential divergence, actually regardless of the precise value of delta 0. As long as it's a positive value, we have negative damping. So we know we have unbounded exponential growth. Okay, so this is really a very important point. So because this tells us really qualitatively we cannot explain with linear theory what happens. We saw that there's obviously a finite amplitude at which the self-excited oscillations saturate, but linear theory just says we have an exponential explosion. If given enough time, the amplitudes will become arbitrarily large. So this is really a qualitative difference, much in contrast to what we did so far. Actually, conservative oscillations and also damped oscillations. Obviously, we have stiffness and damping that depends on amplitude now. That is actually a qualitative difference, you could say. But we could achieve the same effect with another parameter around another parameter setting. So if we change the preload, for instance, we could have a different effective stiffness, and with damping similarly. So the effect, the qualitative effects, if you will, of nonlinearity were not so surprising to us, but this really is something quite unique. So bounded self-excited oscillations can only be explained by nonlinearity, are something inherently nonlinear. Another point that one could make here is that linearization does not always exist, so or is not always possible. So if the force here, this force term, is not differentiable, in particular if it has kinks or is discontinuous, it becomes more complicated. Yeah. So this is the linearization. This apparently doesn't help us really with what is actually going on. So we cannot explain qualitatively what happens. Of course, the possibility is to go to numerical methods. And if you saw, there's a chapter about computational dynamics, so we will deal with that later. And at that point also discuss the important drawbacks and benefits, or limits and opportunities, of numerical versus analytical methods. So what we actually do is use analytical methods to come up with approximations, and we in particular will use harmonic balance and complexification averaging, so two methods that we are already familiar with. And to do this with harmonic balance, to treat self-excited oscillations, this will actually be part of an exercise, while complexification averaging will be what we do now. So that, of course, CXA degenerates into harmonic balance if we are only interested in the steady state oscillations. So we will assume now, in accordance with this approximation, this is actually the same. This Ansatz is the same, where we assume that Q is some approximation QH of T, and this can be expressed as a harmonic oscillation, A e to the I theta e to the I integral omega dt, and theta and A are generally allowed to slowly vary with time in the complexification averaging case. And we just copy at this point the slow flow equations. And now we combine these two. And of particular interest, it is actually the steady state. So we will actually look only at the steady state. That is the most fascinating point. The bounded self-excited behavior. So at steady state, the time derivatives of amplitude and phase are both equal to 0. Now if we do this multiplication here, then actually what we get is this. So the terms that we get here, if we multiply to m omega and exploit also that this basically this 2d omega tilde is actually small d over m, so the effective damping, which is composed of the underlying linear damping and the equivalent nonlinear damping. So this term becomes this here, d plus d equivalent omega a plus the imaginary part of what was written above. So of course we have no external forcing here, but the derivation now is still relevant and useful also for the forced case. Yeah, that's why we do this so in a so detailed way. So omega tilde squared is k over m, so if we multiply by m it's like this, and then minus m omega squared times a real part. Now we combine these two, multiply this by I, this by 1, and subtract the 2. Actually, wait a minute, I made a mistake here. This must be minus real part. So we subtract the two equations. Obviously what we want is that we have basically just the argument here of this real and imaginary part. If we have real part plus I times imaginary part, that's just the argument of these operators here. So with that we arrive at this here. Now I write explicitly the amplitude dependence. And I bring this e to the I theta to the left hand side. On the right hand side is now the forcing term. And I can now say what this is. This is really a term that I know from linear theory, but it is now in its nonlinear extended form because it involves the nonlinear equivalent damping and stiffness. This is the dynamic stiffness actually, S of omega. It is in the linear case, and in the nonlinear case we also have an amplitude dependence. And this here, a to the I theta times e to the I theta, that's just what we see here. This can be interpreted as Fourier coefficient, right? So of QH as the complex Fourier coefficient. So let's call this here Q1. Now in the linear case we have K equivalent and D equivalent to 0. And then this equation here corresponds to what we got in the harmonically forced case in linear structural dynamics. But now we take a different path here. What we do is we consider the autonomous case. So, but because this is important, and we will later come back to this equation when we discuss the forced setting. Just make a frame here. So in the autonomous case, we know that the frequency, capital omega, the oscillation frequency, is simply omega tilde. And obviously we don't have any external forcing. And then if this is 0, and Q1 could then obviously be 0, but that would be the trivial solution, and we know, at least for what we looked at so far, this leads to the unstable equilibrium point. So we can actually follow that generally m omega squared needs to be k plus k equivalent of a. So we can split again imaginary and real part within the bracket. So this would tell us exactly the natural frequency. So actually this is omega tilde. So this is something that that's not surprising to us, because this is the definition of this omega tilde here. If we substitute this in here, omega tilde squared is this sum here divided by the mass. And now this here needs to be satisfied. So d equivalent a I omega tilde a e to the I theta. This has to vanish. And we can have different ways on how how this could be achieved. So yeah, we can have first of all we could have a e to the I theta equal to 0. This would correspond to an equilibrium point. So just as in the linear case, this remains a solution to the autonomous equation. The equilibrium point in the self-excited case is still a trivial solution. What else could happen? We could have omega tilde equal to 0, right? So if we want this expression to be 0, omega tilde could be 0. The mass is always positive in accordance with our assumption. So then k plus k equivalent needs to be 0. This is this actually means that, okay, k at the equilibrium point is maybe not 0, but for a certain amplitude this gets 0. This is possible. What does that mean physically? If stiffness goes to 0 under variation of some parameter, this means that we have a transition from a statically stable to an unstable equilibrium position, right? If we actually have a 0 crossing of this term here, this would mean that for a certain amplitude we have a transition from static to unstatic, stable to unstable static equilibrium point. Okay, that is a possibility. So let's just write this actually down here. Oh no, let's write it not as this, but let's write it like this. Gain of so if we have some buckling under a certain amplitude, this could lead to this situation. And the third option, and this is actually the most important one for what we do in the following, is that the sum here of d plus d equivalent, so the overall effective damping, vanishes. And this is actually this is a change of stability. So either we first have stable behavior and then statically unstable behavior, then this means we have exponential divergence again. Or we gain static instability, then we have an unstable equilibrium point. This is not in accordance with what we actually assumed. So we would have linearized apparently about an unstable equilibrium position, which is not very useful. So the only possibility of these three that leads to bounded behavior, non-zero behavior, is this one. So this is the only bounded oscillations. So finite non-zero amplitude. Now, this is obviously then what we will focus on. And for the van der Pol oscillator, let's get back to our motivating example. There the linear damping term D is minus delta zero, and the equivalent damping can be determined using really this determining the Fourier coefficient. You know that already from the exercise, and actually in the exercise you will do that in a detailed way. Now let's just do this very quickly. So equivalent damping is defined like this: to integrate over 2 pi delta 2 QH squared QH dot times sine tau d tau. And after some algebraic manipulations, we arrive at this expression here, delta 2 a squared over 4. So this equation here, d plus d equivalent of a, is now the following: minus delta 0 plus delta 2 a squared over 4 equal to 0. And this means we can solve for the amplitude now. A can be plus or minus 2 times delta 0 delta 2 and the square root of that. I have no problem taking the square root here because we assumed that both delta 0 and delta 2 are positive, so that is no problem here. And as amplitude without loss of generality, we can assume that it needs to be positive or at least not negative. So without loss of generality, we will always say the amplitude A in accordance with CXA or harmonic balance is non-negative. Okay, because this does not lead to any different solution. It's just we have to shift the phase then in order to get the same results. So this is now the solution that we get here. This is the amplitude. What's also of interest is to see what is the frequency at which the oscillations occur. So we have already the finite amplitude now, which was kind of the primary goal. And now let's see how we get that. So the oscillation is obviously at the natural frequency in accordance with this approximation. So we need to determine this here. And the equivalent stiffness is defined like this: 1 over pi a integral 2 pi QH squared QH delta 2 QH dot cosine tau d tau. That's what we need to determine, and if we do this calculation, we get in fact 0 for the equivalent stiffness. Well, this means that in accordance with this approximation, we just have the linear natural frequency here. So k over m. So this would just be what we define as omega. So this would be our approximation. Let's see how accurate that is. We see here now again the equation of the van der Pol oscillator in its form normalized, so that it just has the two parameters alpha and beta. And in fact it was the ratio that affects the amplitude. So if we vary the amplitude, if we vary this ratio between alpha and beta, we change the amplitude effectively. And what we see here is numerical simulation results starting at a certain displacement and certain velocity, and then we see how, as time evolves, the system behaves, and in fact quite quickly it reaches a limit cycle, so a periodic oscillation. And this is periodic, so it has a certain amplitude, and that will then go on forever. And it is nice to see this also as trajectory in the state space, so the phase plane. And we see that regardless of the initial conditions, so whether we start here at this displacement, 0 velocity, at this displacement, this, we always end up on this cycle here. This is therefore called a limit cycle. So we reach this asymptotically, the trajectories very quickly approach this arbitrarily closely, and then we have this periodic behavior. Now when we vary now this ratio here, we see that the amplitudes will change, and we now compare the results of a numerical time integration, so a numerical method that is sufficiently finely discretized so that we can speak here of a good reference, because there's really no exact solution. And HB or CXA I could also write here. For the steady state case, we see in green the behavior we analytically approximated. And we see that as we increase this ratio here, essentially actually in this case not the amplitudes vary because of the normalization, but if we were to we didn't do this normalization, we would also see that the amplitudes change. And here we see that now for very small parameters alpha and beta, we get here a certain almost elliptic shape. And if we increase now alpha and beta, so the ratio is the same and therefore the amplitude is the same, we see that this limit cycle now starts to deviate from an ellipse. Quite stunningly, the amplitude is still pretty much the same, and our analytical approximation matches well with the amplitude, not so much the time evolution. So quite apparently there are some higher harmonics here. If we wanted to determine these also, with single term harmonic balance, we have no chance. We need another method to approximate this more carefully. With CXA, we can also determine or approximate the transient. We didn't do that here, but it's possible in general. You see here also, as function of this alpha versus beta, the natural frequency or the oscillation frequency, the limit cycle frequency, depends on this parameter also. So for small values where also this elliptic shape was present, the approximation is quite good. But we saw that there is no dependence on these factors here. In fact, the natural frequency is always predicted as the same as constant, and only depending on the mass and stiffness, on the behavior of the underlying linear system, therefore. And we see that this does not hold anymore for larger alpha beta. Now, apparently what we computed here was a limit cycle that's actually stable. So regardless of the initial conditions, we obtain this particular limit cycle. And this is something very characteristic of the van der Pol oscillator. For more complicated systems, generally it is conceivable that we have much more than one limit cycle. And then it becomes interesting to discuss also the stability of these limit cycles. If it is an unstable limit cycle, it is questionable whether you want to call it limit cycle, but still it is an object of interest. And obviously if we get different limit cycles, different solutions for the limit cycle, it is interesting to discuss whether these solutions or these cycles are stable or not. Much like what we discussed in the static case when we discussed stability of equilibrium points. And we will see later examples where stability is not always the case, or not always guaranteed. So let's take a break here and then discuss about the stability of limit cycles. Or more generally, stability of limit states. You could also write, in this case we discuss cycles. You will later also discuss other types of limit states. One other is obviously an equilibrium point. So in order to discuss the stability of limit of equilibrium points, we looked at the energy and looked whether we have a maximum or a minimum of energy. And this is more or less the trick that we do here too. So the argument will be to see whether the dissipated or the energy that is supplied by the non-conservative forces per cycle, whether it increases or decreases with amplitude. If the supplied energy essentially grows more quickly with the amplitude than the dissipated one, then this would be an unstable situation, because as soon as we have a slight amplitude increase, then because the supplied energy is larger than the dissipated one, it leads to a further increase of amplitude and so on. So this will be the main argument. So we will look at the energy that is supplied or dissipated, and this is now what we'll be looking at. So we approximate energy supplied and dissipated per cycle per cycle of oscillation. And we approximate this in fully consistent with our Ansatz. So we now specify this. We say that we have definitely an autonomous system and we have a constant amplitude. So we are looking at the cycle really. In that case we can generalize to this. So QH, the Ansatz, is then harmonic oscillation with constant amplitude. Omega tilde is the natural frequency. It could be cosine or cosine with a phase shift. In the autonomous case, as discussed earlier, it does not matter because the absolute phase is not given by any external means, so it's arbitrary. So it depends on where you say now is time zero, and obviously this does not really matter. So if we phase shift a solution, it remains a solution. So it will be useful to introduce normalized time, so we will do that. So tau is then omega tilde t, and d tau therefore is omega tilde dt. And now we're looking at the energy that's supplied and dissipated, delta E, over one cycle. So the change of mechanical energy over one period of oscillation. That's basically what we wrote down here. This expression here, or actually this expression here, where we said this expression needs to be zero. That's really the change of mechanical energy, counted positive if we have an increase of mechanical energy. We now introduce normalized time, and also first we substitute the expression that we got. And obviously, this is connected to the non-conservative force, QH dot dt. And if we now substitute this normalization, we can instead integrate from 0 to 2 pi FNC QH dot d tau. Actually a factor of 1 over omega tilde now needs to be introduced, so let's shift it here. Okay, now we can further go here and discuss what this actually is. So we substitute this QH dot is then minus a omega tilde sine omega tilde t, and omega tilde t is tau, so I can write this like this: 1 omega tilde 0 2 pi FNC Now I recognize that essentially a omega tilde, this is constant over a period, so this is really something related to the Fourier coefficient, right, of this non-conservative force. And if I look very closely to the definition of the equivalent damping, I see that whatever I get here needs to be this minus pi a So it's this. And now this is omega tilde d plus d equivalent times A. So that's just the definition of damping and equivalent damping and overall damping. So this here can finally be written as this. Okay, so this is the expression for the increase of energy over one cycle of oscillation. Now, if we apply this to the Van der Pol oscillator, the delta E gets what? The delta E gets this here, minus pi. Omega tilde is simply omega. Just copy the A squared, and then we have already an approximation for this. So this is very good. So to discuss stability, apparently we get away with quantities that we've already computed. And we can split this actually into a positive and a negative term. And because it's so simple in this case to split, we can give this a name. So this is the increase of mechanical energy. So this is really the supplied energy. Whereas this here, that's the dissipated energy. Good. Now we need to discuss the zero crossings of the energy balance. So basically, at what amplitude is supplied energy equal to the dissipated energy, and how are the gradients basically? How is the is supplied energy growing more quickly than the dissipated one, or the other way around? So we make a diagram essentially and we do so for this particular example of the Van der Pol oscillator, and then later discuss more general cases. Okay. So we plot here the change of energy versus amplitude. And apparently we have here a quadratic parabola and a fourth order parabola. So let's say we make this supplied energy the standard parabola, the quadratic one. So then it might look like this, but actually not. Not dashed, but more like this. And on the other hand, so this is the supplied energy growing with A squared. And the fourth order parabola is smaller first, obviously, then increases more quickly. So we do have here 2 points where actually these two energies coincide, and that's this point here. and it's also at this point here. So yeah, let's discuss the stability here. So in this range here, the supplied energy is larger than the dissipated one, and here it's the other way around. So delta E as smaller delta E D. So if the supplied energy is larger than the dissipated one, and I have a certain amplitude already, then this means the amplitude will further grow. And here it's the opposite, the amplitude will decay if the dissipated energy prevails. And then it's quite obvious that this is a stable point here, this is the stable limit cycle. So this limit cycle is stable, and this is in agreement with our observations from the numerical simulations, that we reach this limit cycle no matter what. And as opposed to that, this will be an unstable equilibrium point. So arbitrarily and therefore inevitably small perturbations will lead to a situation where we go away from this equilibrium position. And then reach this stable limit cycle. Now, this was just this one case. There are other cases that are conceivable that may look a little bit more complicated. Where we have multiple limit cycles in particular. Now, yeah, one possibility here would be that, for instance, the supplied energy looks the same. Still a parabola. Sorry, it's more steep than I wanted. So maybe it looks, not nice. Okay, maybe like this. And the dissipated energy looks like this. So first, let's say first it is zero, and then at some point it increases linearly. So here we have now multiple intersections. We have this, and this point. And if we do follow the same argument, amplitude increases here, here it decreases, here it increases again. And this would then be an unstable equilibrium. Equilibrium point still. This would be a stable limit cycle. And this needs to be an unstable limit cycle. You could also say it's a stability limit because beyond this point the amplitudes would grow, it looks at least unboundedly. If the trend stays the same, then supplied energy will grow and grow and grow, and therefore and dissipated energy will always be smaller. Then as soon as we have an amplitude beyond this point, beyond this A star, then we will not have any stable oscillations anymore, any bounded oscillations. So this is interesting because only in this range here we have stable behavior, or we have bounded behavior. So stable in the sense that as long as we have small perturbations, we remain arbitrarily close to this situation. Whereas if we are beyond this point, this is not the case. We go away from this situation very quickly. So beyond A star, we have unbounded growth of oscillations. I should put in brackets with this model, because obviously nothing will ever grow unboundedly, at least not on Earth, and therefore some other form of nonlinearity that is probably not modeled here will come into play, and in the worst case it means structural failure, which is also nonlinearity because of the inelastic deformations that then happen. Now this is not just a mathematical abstract example, but actually this is quite relevant, because this delta ES is nothing special. This is just a negative damping. Negative viscous linear damping leads to precisely this quadratic parabola shape of the supplied energy. And the dissipated energy, you might already see that this corresponds to elastic dry friction. So something that we already discussed. Up to a certain amplitude, we have only sticking, so no energy is dissipated, and in this range, once we are sliding, the energy will increase with the amplitude linearly. So the energy that's dissipated in the frictional hysteresis cycle increases linearly with amplitude, and that's precisely the situation shown here. So if we have self-excitation, for instance, due to an aeroelastic instability, plus we have some damping that's dominated by dry friction, then this is actually the typical behavior. Now, to show you also another case, let's say the dissipated energy now has this linear type, this sort of linear behavior, and because it's linear viscous damping, we get a parabola for the energy change. Now this dissipated energy shall take this form, and let's assume we have supplied energy like this. At some point it takes this form. Then again we have here an intersection, there we have an intersection, and another one. Now the interesting point about this is that for small amplitudes we go here, right? We have dissipated energy larger than supplied one. So we have a locally stable equilibrium point. This is a stability limit in a sense, or this is at least an unstable equilibrium point, or an unstable limit cycle, sorry. I call it LC limit cycle. And this here again would be a stable limit cycle. Okay, because yeah, here amplitudes grow, here amplitudes decay again. So interestingly, the behavior would be for small amplitudes we remain in the stable equilibrium point or go again back to this. But as soon as we have amplitudes larger than this threshold here, then amplitudes grow until this point, until we reach this limit cycle. So this is an interesting situation because linear theory would then tell us that this equilibrium point is stable, but in effect, if there's an sufficiently large, not zero, not vanishing small, but finite, but perhaps small initial perturbation, so some perturbation that gives us the situation that we have amplitudes larger than this threshold, then actually the vibrations grow until this limit cycle. And I mean the lengths of these sections could be arbitrary, right? This threshold here, that beyond which we reach this stable limit cycle, could be very, very small, could be very close to the equilibrium point. So linear theory gives us stable, predicts stable behavior, but actually the threshold is very small until which we reach a perhaps very large amplitude limit cycle. So this is also an interesting characteristic behavior that we may get. So we don't need an unstable equilibrium to have limit cycles. And limit cycles reached for sufficiently large initial perturbation. Good. The question is now, can this actually happen, or is this, for instance, is this maybe just a theoretical situation? But in fact, we will see that this actually can happen for pretty much the model that we already discussed. So this is the example that I promised, that behaves pretty much like just indicated, with a stable equilibrium point, but a limit cycle coexisting for some parameter ranges at least. So it's again an airfoil in a wind tunnel, has a certain mass, has a certain stiffness, but now we attach the viscous damper in the direction of motion. So it's still restricted to have just this plunge motion, no twist. So we get this very simple force balance, and now the nonlinearity is taken into account coming from this lift coefficient. So the lift coefficient is now developed further into a Taylor series, so we take into account larger velocities. Okay, so that this expression cannot be linearized anymore, and then essentially we get this we can develop this, for instance, into a 7th order power series, and then we can normalize the equation so that this is helpful to us. And this can be brought into this form. So on the left hand side we have more or less the standard form of the damped single degree of freedom oscillator, and on the right hand side are the aerodynamic forces. And I expressed this the aerodynamic force coefficient here using this ratio here. If the velocity, which is now the important parameter, this will determine whether we have stable or unstable behavior. V over V critical. If V reaches V critical, what happens then in the linear case? So ignore the higher order terms. Then we have here 2D Q prime, and on the right hand side 2D Q prime. So the damping, overall damping, is 0. If V is smaller, then the damping here dominates and the effective damping is larger, is positive, larger than 0. So we have a damped situation. If V is larger than V critical, we have an unstable equilibrium point. But this is just linear theory, right? So as soon as we have reached this threshold, we expect either a stable equilibrium point or an unstable equilibrium point, giving rise to exponentially growing amplitudes. Now what actually happens is this here. So you see here the overall damping, so the linear viscous damping plus the equivalent nonlinear damping. And sometimes it is easy, sometimes it is much more difficult or not reasonable to split into supplied and dissipated energy. So this wasn't done here either. And in fact, sometimes it's easier to plot directly the damping, the overall damping, instead of the energies. And this leads to this depiction here. So first we have, for a certain amplitude, we have positive overall damping. Then we have some range where we have negative damping, then positive damping again. And this, again, the same argument can be done. So this needs to be an unstable equilibrium point, because if we have slightly larger amplitudes will further grow. Here they will further decay until we reach the equilibrium point, and so on. And this is currently at this parameter range. So we are subcritical. That's the important point here. We are subcritical. So according to linear theory, the equilibrium point is stable. So if we were to design, for instance, an airfoil against flutter, you would say, well, I'm in the safe zone here. I just need to keep away from this point, from the critical speed. But interestingly, this might be dangerous, because even if we are in the subcritical range, we might have some perturbation that leads to amplitudes larger than this threshold, and then we will reach this limit cycle amplitude here. And perhaps this is severe, perhaps it is not severe. That needs to be assessed, but this can only be done with nonlinear theory. So this is a quite typical situation. One speaks of a subcritical Hopf bifurcation, and this is particularly dangerous because it is so unexpected that if linear theory says it's stable, that nonlinear theory actually shows that there is something possibly dangerous coexisting. And this can also be shown here, these stable and unstable limit cycles in the phase plane. So we have here the stable limit cycle, and this is reached for larger amplitudes. And you see that you go either into the spiral inwards to this equilibrium point, or spiral outwards to this stable limit cycle, whether you are inside or outside this stability limit. And if you actually go further to this supercritical point, there's 1, 2, 3 limit cycles coexisting and the first one is stable, then we have an unstable one and another stable one. So we have actually coexisting limit cycles. Now we have also further examples of self-excited oscillators, and here just some of them. So one is actually the tilting bucket pendulum. So what happens here is that we have some water coming out of this this faucet, and you have here a bucket that is filled with this water, and then because of if the water becomes too heavy, in fact, if mass times the lever up to this this point here is larger than the mass times this here, then this pendulum loses its stability and will tilt. Then this water will flow out, of course, and then the mass here is heavier, so that the pendulum wants to get back to its initial position, and then the process repeats. So this is an example. Here the energy comes from the potential. So basically the potential energy is here the one that the system receives by its own dynamics. So it stores the potential energy, then relieves it, and then the process repeats. And during this process, of course, some potential energy is converted into kinetic energy and so on. A dripping faucet can be described as self-excited process. An electrical bell is another example. Actually, when this circuit is closed, then some current flows, and the current leads to this coil here will induce an electromagnetic field, which then wants to attract this part of the bell, and then this leads to the situation where this bell is impacted, making a noise. And during this, because this then is connected to this, then moves to the left, the circuit opens, and because it opens, the force here due to the electrodynamic force here goes to 0, and because this bell then has some inertia, it goes back to its initial position, closing again the circuit, and then the process repeats. Wind instruments you can explain also with self-excited oscillations. A geyser is something else. So all of these are not really purely mechanical examples. I give you more mechanical examples in a minute, but just to see that self-excited oscillations are really very, very common in natural science and engineering. And in fact, if I can recommend going to Iceland, because you can then find the geyser that's actually given the geyser the name. The geyser is called geyser. And the simple model of this is that there's some heat source, obviously, geothermal activities. It's a geothermal activity, so there's some heat source. And imagine that you this wants to evaporate. This wants this expands in volume. You get some gas here, but it cannot go to the surface because it has a lower density. So it actually takes up the volume here because this pipe is curved in this way, and then this further goes until this bubble, this gas bubble, grows larger and larger, and at some point it can actually go to the surface and takes a lot of water with it, and in reality this looks like this. So hopefully this works. Yeah, and leaves the large fountain. Very impressive if you stand beside this. Now I wanted to give you more technical examples, and actually these are technical, but some are not so technical, some are more in your everyday life, and hopefully when you now see reality, you now see reality with a different way, because hopefully now you see self-excited oscillations everywhere. So many self-excited oscillations are actually friction induced. So there is some dry friction, and this explains actually brake squeal, squeaking doors, the operation of a violin, swinging glass, trams of a curve, making some noise, chatter of machines, squeaking windsweep wipers, just to name some examples. And a very simple model is actually this stick-slip oscillator model. So friction-induced self-excitation is not limited to this. There are some other forms of friction-related and friction-induced self-excitation, but this is probably the most basic form. And this can be explained by this spring mass oscillator here, which is now exposed to some dry friction, because we have here this band, this which goes round and round, and we assume that this band has a certain velocity that is imposed, q dot 0. And this this is the velocity that is imposed. And now you can imagine, well, probably for some ranges we have sticking, for other ranges we have sliding, depending really on the dynamics of this system. And what we also assume, and what is important actually for the following, is that we assume that this tangential force here, this friction force, depends on the velocity in this way. So actually we have the largest force for sticking case, where the relative velocity is 0. And then for larger relative velocities, the force actually becomes smaller. So the sticking force is larger than the sliding force. This is important for this model and for understanding slip oscillations. Now let's plot here the different parts of this kinetic and kinematic parts of this oscillation process. So let's assume a certain harmonic oscillation for q dot. So let's assume it does oscillate, so that also the velocity then takes this harmonic form. Then we have, of course, a certain q dot 0. Q dot 0 is the imposed velocity. If I orient the coordinate system like this, actually the relative velocity is the sum of q dot 0 and q dot. So like this. So we are here, and we oscillate basically around 0, around q dot 0, not around 0. That's the point. So we reach, we have this forcing here. This forcing assumes has a mean value, and it assumes smaller values in this part of the period and larger values in that part of the period. Now the power that we need to assess is actually the product of the force times the velocity. So ft q dot is the power, the instantaneous power, and we see that this is positive here. So energy goes actually is actually dissipated. So in this conversion or in this orientation, the force here is plotted in the opposite direction of the motion. So this would, if it actually goes in this direction and points negative in the opposite direction of the velocity, it actually dissipates power. So this is the dissipated power, and it's positive in this range. And here, obviously, the average value of the force is smaller than in that range. So here we have a negative power, but the average value here will be larger in magnitude than here. So the area in this part here is larger in magnitude than the area here, and therefore the average value, which is basically just the integral here, the average value will then be negative overall, taking overall this dissipated behavior. So quite apparently, what will happen is that the oscillations, the equilibrium position is unstable. We will see some negative dissipated energy, so the vibrations will grow, and this is basically a short explanation for stick-slip oscillations. So let's just do a short recap here of self-excited oscillations. We have here the autonomous single degree of freedom oscillator. In its general form, the core idea was to split this quite general restoring force into a conservative force and a non-conservative force. And the energy change is just due to this non-conservative term here. And we also notice that linearization, if it is possible, only gives stability in an infinitesimal neighborhood. It doesn't explain bounded self-excited oscillations, and what we also saw, it does not lead to a conservative design. We may have, under finite perturbation, a large limit cycle amplitude. Yeah, and then we can approximate this. We can approximate the limit cycles with harmonic balance, also with complexification averaging, but this wasn't so much of concern here. So we can have always the trivial solution, but we're interested, of course, in the non-trivial limit cycle. So static equilibrium point is always the trivial solution. We can have non-trivial limit cycles that are governed by this, by saying that the overall damping ratio, or the sum of linear and nonlinear equivalent damping, has to vanish. And then we can also assess the stability based on analyzing this energy expression, basically the energy change over one cycle of oscillation, and how it depends on amplitude we can then discuss. At this point, here's just some summary of hints how to determine Fourier coefficients related to equivalent damping and equivalent stiffness. And there are some symmetries, first of all, that are here defined: mirror symmetry, rotation symmetry. For instance, cosine is a mirror symmetric, sine is a rotation symmetric function. And first of all, you see here that you can always split these, and there's this integral rule that if you integrate over 2 pi over a full period, mirror and rotation symmetric, it gets 0, and product rules that apply here. There are some rules here that help you when actually your task is to determine the Fourier coefficients. First of all, you can take shortcuts if you exploit symmetries. And here are some further hints. The splitting, and it's interesting to see that the non-conservative forces can actually affect the stiffness, but conservative forces do not damp. That's a general rule that you can follow, and you can exploit here some symmetries as it is shown here in order, and here's some examples where the equivalent damping, for instance, is 0, and you can actually already see this by the form, by the symmetries in the form that we have here. By some further guidelines. You don't need to know all of these by heart. That's not really the idea. It's more that you understand what's the reasoning behind this, and then you basically can exploit this, for instance, by not having to compute every single term in the exam, for instance. And here are some integral tables that may be useful, especially for piecewise defined nonlinearities or piecewise smooth ones. There's also some proof here, It's also a good exercise for homework, actually. All right, that was everything for self-excited oscillations for today.